Welcome guys, hope you're doing fine and enjoying my videos, and as you can see here, I'm not trying to explain you about a birthday party, but what do you remember, what does it remind you of whenever you step into one? I'm not talking about the birthday cake, dismiss the mouth watering. I'm talking about the balloon, specifically a helium balloon. Have you ever wondered why they rise up and just do anti-gravity stuff? Well, you might just say buoyant force, like the air around. An equal volume of the air around would have more mass and therefore more weight, so it would exert more buoyant force than the balloon's weight, so that's what causes it to rise up. Well, nothing's wrong with this theory, it's all fine, but I decided to not be so straightforward, and so I came up with another theory which uses a math theorem. Let's see what it is. Before we do that, let's see another example. So we have 4 liquids over here. So the density of oil is like around 0.8 grams per ml, or grams per centimeter cube. So its relative density is 0.8. And we have water, which has a relative density of 1, or 1 gram per centimeter cube. And salt water has a density which is a bit more than that of water. And you've probably done this experiment when you were a kid. You just drop a grape into water, it sinks, but then you just stir some salt, mix it very thoroughly into the water, and then now if you drop a grape, it'll probably float. And then here we have mercury, which has a very high density of around 13.6 grams per centimeter cube, which is actually very high for a metal. It is greater than that of most metals, although it is a liquid. Now, here's what I want to do. This is my math way of approaching this. So, this is a very famous, or maybe not so famous, but very interesting theorem, I would say. So, we have a series of A1, A2, A3, so on, in ascending order, and then we have another ascending series of numbers here. Well, in this case, they're positive, so there's nothing to worry about. And now, let's say you just shuffle this series. It becomes what we call a permutation in math. And then you just multiply whatever value comes here with this one, whatever value comes here with this one, and then so on. And then add up all those products. Whatever you get will always be greater than this sum. Well, greater than or equal to, unless you just decided to completely just flip this sequence and then you end up with an here, an minus 1 here, and then you just go on till a1. So basically this is the minimum possible such value. Now, how is that related to, well, this thing, this density issue? So we know that potential energy is equal to mgh, and since g is a constant, it doesn't really affect what we do right now, as long as it is not negative. So since g is positive, well, we can just consider m and h, which is the height, and here m is the mass, which is basically proportional to the density, so we're just going to be considering the density over here over the mass. So we're going to be taking these two series, density of the liquids in ascending order and the respective heights which they may attain. Now, make sure that both these series have the same number of values, or else, well, you'll go crazy for what you might need to do for the last few extra terms. So, yeah. We do have the same number of values in each case, because for each liquid there is a specific density value and a specific height which they may attain. So now, one thing which you have to understand is a conservative force, for which potential energy is associated with, will always try to decrease the potential energy. So nature always prefers bodies which have lower potential energy, not total energy, specifically potential energy. So that is why we're going to explore this thing using that fact. So now just take the first series as the densities, as I mentioned, and the second series as the heights. And now you want the minimum possible potential energy. So what do? You just multiply this term with the last term here, the second term with the second last, the third with the third last, and so on. You just keep multiplying, and that's exactly what's here. So as you can see here, this is how we can minimize the potential energy. So as you can see in the previous slide, for example, here we have a low density substance which occupies space at a greater height than all the other liquids over here. So here what we're doing is we're assigning the maximum height to the minimum density, which is what we're supposed to do according to this theorem. And then we just go on taking the next higher density with the next lower height, and then so on. That's it. So this is why we get this kind of order. And this theorem, well, it's not just for proving this physics trivial problem, which we see everywhere. It is also very useful if you're applying for math Olympiads, especially the national level, because these kind of proofs are very common, and inequalities are a significant part of them, honestly. So this is why this theorem proves to be very useful in proving this. So it is not just a math theorem, you can actually apply it to physics stuff. So I hope you enjoyed this video. Thanks for watching. Goodbye.